Okay, 8.4, area between curves with respect to x. Okay, so I'm drawing a function f like this, and I'm drawing the same function here. I'm going to draw a function g now. Let's see, I want g to kind of look like this. Okay, and I'm going to redraw the same type of g here. Okay, now when we're talking area between curves in this section, we're talking about, oh, this is it. Hold on. Let me move my b. I want my b to line up with the point of intersection, which is like right here. Okay, I'm going to try to find the area between these two curves. So between f and g, that's what I'm looking for. Okay, so imagine my b was lining up at each of these points, even though it's totally not at all. Okay, so consider the first one where I have the graph of f. If I wanted the area under this curve, this whole entire thing, I would represent that as the area from the integral from a to b of f of x dx, and that would give me the area under that curve. Okay, now for the next one, if I integrated a to b g of x dx, I would get the area from a to b from the curve to the x-axis. Okay, now if I only want the area between the f and the g functions from a to b, so just this little space in here, I would start with the area under f, and I would get everything under here. And I don't want to count this part, so I would subtract off the area under g. So that would give me the integral from a to b, and I'm doing f of x, because that's the one on top, minus g of x dx, and I should be left with just the area between the curves after I've done that. Okay, so here's the area between two curves formula. We're doing this with the assumption that f of x is higher than g of x, as it was in the picture, or at least it was on the interval a to b. Okay, f of x is greater than g of x on the interval a to b. Let's see, let's do fancy. For all x in the interval a to b, f of x is greater than g of x for all x in the interval a to b. Okay, then the area under the curve is going to be the integral from a to b of f of x minus g of x dx for the reason below. And the main thing to keep in mind is that this one has to be the top one. This one has to be the bottom one. Okay, let's look at one for real to see what we're doing. Okay, it says find the area bounded by y equals x squared plus 2, y equals negative x equals 0, and x equals 1. So let's just graph this real quick. So y equals x squared plus 2 is a parabola. Looks something like that. Okay, y equals negative x, y-intercept is 0, slope is negative 1. Okay, and then I want it bounded by x equals 0, which is here, and x equals 1, which is here, which leaves me with the bounded region in here. That's what I'm trying to find. Okay, so let's use what we were looking at. Okay, if I want the area, I want the integral from a to b. I'm going along the x-axis. I want the integral from 0 to 1. And then I want to do the top function, the higher function minus the lower function. So this is the upper function, which is the x squared plus 2. And then I want to subtract the lower function. This is the lower function, that's the negative x. And I'm integrating with respect to x. Okay, this is my setup. Let's do it. Let's try to actually figure this out. Okay, if I do the integral, I get x cubed over 3 plus 2x. Negative x is positive x, so this is really x squared over 2. And I'm evaluating this from 0 to 1. Okay, let's plug in 1. 1/3 plus 2 plus 1/2 minus a big fat 0. Okay. 1/3 plus 1/2. 2 6 plus 3 6 is 5 6. So I get 2 and 5 6. 2 and 5 6 is 17 over 6. But let me think. 2 and 5 6. This does look like 2 and 5 6. I have 1, 2, and this could make 5 6. So that seems reasonable that this is the area between the curves. Okay, let's try another example where they did not give me the graph. Okay, so for example 2, it says find the area bounded by y equals 2 minus x squared and y equals x. Now the fact that they said it was bounded means it's like a closed region. So they must intersect somewhere because they didn't tell me where to take the integral from. So first thing I'm going to do, I'm going to figure out where they intersect. Which means I want to see where they equal each other. Let's set them equal to each other. Okay, I'm going to move everything right. So positive x squared, positive x, negative 2. So I have that at x equals negative 2 and x equals 1, these two functions are intersecting. So if I want to find the area, that's going to be the integral from negative 2 to 1. And then I want to do the higher function minus the lower function. Now, which one's higher and which one's lower? Okay, well, if you know how to graph them, you could sketch it real quick or you could imagine it in your mind. So let's just think about this real quick. That's going to be 2 minus x squared is a little parabola. Y equals x is going this way. They're intersecting at negative 2 and 1. So if I look at the picture, the parabola is higher, which means that the 2 minus x squared is the higher function. 2 minus x squared. And I'm going to subtract the lower function, which is the x. Okay, now what if I couldn't graph it though? Okay, if I couldn't graph it and I didn't have a graphing calculator on that I was allowed to use, I know it's between negative 2 and 1 that I'm trying to see which one's higher. So I could just randomly pick a number between negative 2 and 1 and then see which one of these functions is actually higher. So say between negative 2 and 1, I pick x equals 0. Okay, at x equals 0, if I plug it into the first function, I get 2 minus 0, I get y equals 2. Okay, for y equals x, if I plug in 0, I get y equals 0. Since at x equals 0, this function is higher, and they're intersecting at negative 2 and 1, meaning they only cross at those points, then this must be higher the entire time. So I could use this to figure out which one's higher. Okay, but either way, I have this set up. Do I want to solve this for L? No, I'm going to put this in my calculator. Okay, I'm going to put it in my calculator, and it tells me that it's going to equal to 4.5. Okay, let's consider another example. We're practicing the setup a lot because that's going to be the hard part. You guys already know how to integrate. Okay, so example 3, it says set up the integral to find the area in the first quadrant that is bounded above by y equals square root x and below by y equals x minus 6. So this line up here is y equals square root x. The one down there is y equals x minus 6. Okay, so I want to find the area of this entire shaded region. Okay, let's look at this real quick. Okay, I want to do the higher function minus the lower function. Okay, this is definitely the higher function. It's the higher function all the way, the whole time it's bounded. Square root x is always the higher function. Now let me look at the lower function. Okay, now right here, the lower function is actually the x-axis, or it's y equals 0. Until we get to 6, and then the lower function becomes the y equals x minus 6 line. So there's actually two different situations going on. Okay, and it changes when I get to 6. So from 0 until 6, y equals root x is the higher function, but my lower function is actually y equals 0. Okay, then once I get to y equals 6, cross this imaginary line, the upper function is still y equals square root x, but now my lower function is y equals x minus 6. So I need to set up two different integrals because my top and bottom functions are not consistent the entire time. The entire time I'm measuring the area of the curve. Between the curves, whatever. Okay, so what was it? From 0 to 6. 0 to 6. The higher function is the square root of x. Okay, the lower function is the x-axis, which is y equals 0. So this is like square root of x minus 0. Do I have to write the 0? No, not at all. Okay, now let's go to the next piece. Okay, now the rest of this area goes from x equals 6 until x equals 9. So from 6 to 9, the higher function is the square root of x. The lower function is now this x minus 6. So I'm going to subtract x minus 6 and put it in parentheses because you're subtracting the entire function. Okay, this is my setup. And then I could evaluate it by hand or in my calculator. Just be careful also when you're subtracting. Make sure you put that second function in parentheses because the negative is going to distribute and it might mess up your values. Okay, let's look at 4. We're ready for a calculator active problem. Okay, same idea. Find the area bounded by the curves y equals ln x and y equals 1/2 x minus 2. Okay, I do want to see where they intersect. That's just like on 2 ones before. So I want to see when ln of x is equal to 1/2 of x minus 2. Now, do I want to solve this? No, I have a graphing calculator. I'm going to use my graphing calculator. Let me graph them and then see where they're intersecting. It's also going to help me determine which function is higher than the other. Okay, here's my graph right here. This is ln x at the top. This is 1/2 x minus 2 as the lower function. So that helps me figure out which one was higher already. I want to find this intersection and I want to find this intersection point. And I'm going to do that by doing second calc, and then I'm going to do intersection, which is 5. Okay, and then I'm going to make sure I go to the first curve, and then I'm going to go to the second curve, and I'm going to get those 2 points where they're intersecting. Okay, now I did the first point of intersection, and I got 0.1455, and I'm going to use this answer in my integral, so I don't want to round it yet. So rather than round it, I'm going to have the calculator store it as a letter. So immediately after I find the intersection, I'm going to quit that screen. And then on the bottom, just above your on button, is a STO with an arrow. I'm going to store this, and I'm going to say alpha, and then I'm going to pick a letter, like A. Okay, and then it's going to store that value as A, and I can type A, and it will give me the number. Okay, I'm going to do the same thing with the other x-intercept, which was about 8.2109, but it had a bunch of other decimals, and I'm going to store it because I'm going to use it in another part of the problem, and if I don't keep it, I have to remember it the whole time. Okay, hold on, I'll take a picture. Okay, after I hit store as A, it looks like this, and so now every time I type A, it's going to pull this number up, plus some extra decimals. Same, if I stored the second value as B, every time I call B, it's going to pull that number up. I'm going to set up my integral, and then I'm going to use that to pull my values up so I don't have to, 1, type it in, and 2, so I don't mess up my rounding, because the rounding is very easy to mess up. When you use it, when you keep using it and using it, it gets further and further off. Okay, so let me see what I'm trying to do. I'm finding the area between the curves. So that's going to be, the area is, I'm going to go from this to this. Since I wrote here that I'm going to call this A and I'm going to call this B, I'm going to write from A to B here. As long as I have written on my paper what A and B represent, I can do that. Or you could write the approximations here. This is from 0.1455 and a bunch of other stuff to 8.2109. Okay, the higher function was this blue one, which was the ln x. And then the lower one was the 1/2 x minus 2. Remember to subtract the whole thing. You could distribute the negative or something. Okay, that's what I'm going to do to calculate the derivative. Okay, and then when I punch this in my calculator, because my calculator knows what a and b are, I can actually put a and b as the boundaries in my integral. Okay, so here's what I wrote in my calculator. My integral got cut off. I did the integral from a to b of ln x minus 1/2 x minus 2, the quantity dx, and because I had stored the a and the b, my calculator remembers it. And now I am going to round it because I'm on my final answer, so I'm going to keep 4 decimals. And you can truncate it or you can round it. Either way is fine. Okay, so this is my result. If I had rounded these, used these rounded values, I would have gotten a different number here. It would have been off and I wouldn't have gotten full credit. It wouldn't have been as accurate. Okay, now once you store your A and B here, it's going to keep it as A and B until you rename your A something else or until you reset your calculator, which we do sometimes when our calculators are not behaving well. Okay, example 5, which we're going to do 2 ways. Okay, so it says let R be the region bounded by the graphs y equals 2 square root x, which is this one, and y equals x squared over 4, which is this one. If the line x equals k divides R into 2 regions of equal area, what is the value of k? Okay, x equals k is a vertical line. So they're trying to figure out there must be some vertical line that divides this perfectly in half. Okay, so let me just put it somewhere random. Well, not really random. That kind of looks like it's in the middle, right? It doesn't have to be in the middle. But this is x equals k. It's not a 2, it's just randomly placed there. Okay, I want to figure out when this area is equal to this area. Okay, let's start with the area on the left. Okay, I want the area on the left equal to the area on the right, so I'm actually taking the area from 0 to k. I just don't know exactly where k is yet. Okay, the upper function is the 2 root x, and I'm subtracting the lower function, which is the x squared over 4 dx. Okay, I want this to equal to this area over here, which is going from x equals k until 4. And I still don't know what k is, which is why I'm putting k here. So from k to 4, 2 root x is still the higher function. X squared over 4 is still the lower function. I'm going to set these equal to each other and just try to figure out what it is. Okay, let me do the antiderivative. Oh boy. Okay, this is 2 to the 1/2, so that's 2. Why did I put an equal sign there? 2. This is x to the 3/2 divided by 3/2, so times 2/3. Minus x to the 3rd divided by 3. 3 times 4 is going to be 12. Okay, and I'm evaluating this from 0 to k. Okay, now the antiderivative on the right should be the same. I'm just doing a different boundary. So 2 times 2, that's 4/3. I'm just copying the answer on the left. But now I'm going from k to 4. Okay, let me plug in k on the right side. So I have 4/3, k to the 3/2 minus k to the 3rd over 12 minus, and then if I plug in 0, it's going to be a big fat 0. Fair. Okay, now let me plug in 4. That's 4/3. 4 to the 3/2. Square root of 4 is 2. 2 to the 3rd is 8. 4 to the 3rd is 64 over 12. Minus 4/3 k to the 3/2. Okay, now I'm going to do this with my calculator. So depending on what you find more terrible, algebra or typing, I'm going to just go ahead and type this in for my y1. I'm going to type this whole thing in for my y2, and I'm going to see where they intersect. And then I can solve for k. If you'd rather simplify it first, you could simplify it first and try to solve it or make it nicer. I'm just going to plug it in. Okay, if I do that, I get k is about 1.7641. Okay, and it wasn't a pretty way to do it, but it does work. Okay, let's consider if there's another option for how we could do this. Okay, same idea. I want to figure out what x equals k is, so it divides this into 2 equal regions. Okay, so we could think about this different and think like, okay, what's the whole area of this thing? And then we could just divide it in half and then try to solve for k that way. So if I think about it that way, then the entire r, here let me write r actually, r equals the integral from 0 to 4, because I'm taking the entire area of 2 root x minus x squared over 4 dx, and then I'm going to have my calculator tell me what the entire area is equal to, which is 5.333, repeating. Okay, which means if I want to divide it in half, I only want half the area. And then I can figure out what k is. So from 0 to k of the same function, I want it to equal to half of 5.3333333, which is about 2.66666. Okay, I'm still going to do the antiderivative, which is going to be the same. So let me just copy it from above. So it's going to be 4/3 x to the 3/2 minus x to the third over 12. And I'm still going to evaluate it from 0 to k, but this time I'm going to set it equal to 2.2 2/3. Okay, I can still use my calculator to solve this, but you might think it's easier one way or the other. Let me plug in my k. Okay, I'm going to plug in 0, 0 results in nothing. So I'm going to go ahead and graph this, see where they intersect, and then I'm going to get the same k value as the previous. So it's up to you how you want to think about it, but that is a problem that comes up sometimes on the test.